Okay, so we're going to actually prove some things today. First, let me mention some very basic facts about parabolic equations in the context of certain subdomains that we're going to be working with. Remember, we have this graph sigma. It's the graph of a parabolic Lipschitz function. And suppose we look at some box I, some parabolic cube, some elongated, right? We elongated it vertically. We intersect I with the domain omega to get some subdomain, all right? And this subdomain, the boundary of the subdomain, we divide into several different parts. This is a standard parabolic thing. Okay, so this part is, that looks like a beta. I want it to be a script B. B is the so-called bottom boundary. In other words, this is the initial time boundary, right? So for this subdomain, remember time is running this way from left to right. So this is the initial time boundary, all right? And the other parts of the boundary are called a lateral boundary. So notice that there's more than one part here. There's, for the subdomain, this part of sigma itself is part of the boundary. That's S intersects sigma. And this part up here is S minus sigma. On this part, we don't really care about, okay? So there's something called the parabolic boundary. Which we'll denote as dp of omega. And let me not call it omega. The subdomain, let's call it for now, I don't know, omega tilde, okay? The parabolic boundary is B union S, okay? Bear in mind this is a little bit deceptive picture because I've drawn it with only one spatial dimension. If we had it with two space dimensions, imagine a cube, a three-dimensional cube here, and then the lateral boundary consists of a face here and a face on the backside too, okay? All right, and so this is where we specify the data in the initial Dirichlet problem. We specify data on the parabolic boundary. Okay, so initial data gets specified on B, and the lateral data, not surprisingly, gets specified on the lateral boundary. Okay, all right, and also we have a weak maximum principle. The weak maximum principle in contrast to the elliptic case, doesn't involve the entire boundary, but only the parabolic boundary. Okay, so if you have a solution U, H of U is 0 in this subdomain omega tilde, and U is continuous up to the boundary. Let me say it this way. Up to the boundary on omega tilde, so an omega tilde closure, then the weak maximum principle is that the sup on omega tilde of U is less than or equal to the sup on the parabolic boundary. Yeah, okay. Think of it as a non-negative solution, but, well, it's a true statement even if it's not non-negative. Okay? All right? Okay. So with that digression in hand, let's prove a result. This is from Caffarelli and Salsa. And it's an improved backwards Harnack inequality. And remember, I'm using BH to stand for backward Harnack. Remember, we stated last time without proof, I just invoked the result from the paper of Fabes, Groffel, and Salsa. There's a backward Harnack inequality that applies when the data vanishes on the entire lateral boundary, that is on all of S. Okay, so this theorem is going to allow, under a little bit more restrictive circumstances, for us to assume only vanishing on sigma, but not on the rest of the lateral boundary. Okay, so the hypotheses are these. Let's let, as usual, we have this fancy notation for a point x naught xt. This is going to be on the boundary, on the original boundary, on sigma. Okay, we're going to have a non-negative solution bounded from above by 1. And this is going to be in omega 2r, which is omega 2r centered at this x. So in this picture, now let's take I to be I2r centered at x. So this is the point x. Okay? And so the omega tilde that I've written here is now, if you'll forgive me for doing this, I'm going to turn this into omega 2r. Okay? All right. Okay, and so we assume further that H vanishes continuously on delta 2r. Remember, that's I2r intersects sigma. So it's going to be vanishing here, but we're not going to assume vanishing on the rest of the lateral boundary. Okay? All right? Not necessarily on S minus sigma. Okay? All right, and then the conclusion is that, if I run myself out of room, that H of the time backwards point A r minus of Z is less than or equal to, and again, the implicit constants, unless I specify otherwise, they're only depending on dimension and m naught, which was, remember, capital M naught is 1 plus the parabolic Lipschitz constant for the graph sigma. Okay? U of AR plus, whoops, I want a lowercase r here, of Z. Is this getting hard for you guys to read? And this is for all r, little r less than capital R over 2. And Z here in delta R with the same center, delta R of X. Okay? So what's going on here is that, all right, this is I2R. I've kind of cluttered up my picture, but if you'll forgive me for this. Then we have I sub R, and then we're saying that inside here, if we take some little r less than capital R over 2, we have, and these are the time backwards and time forward points, then the time, I said it wrong. I want it like this, because the other thing is just the standard Harnack inequality, okay? That they're equivalent, all right? All right? Oh, thank you. This is definitely H, thanks. Yeah, there is no U at this moment. It's just H, thank you. Okay. Okay, so let's prove this. Okay, so of course this direction is just a standard Harnack. Standard parabolic Harnack. Okay, so we don't have anything to prove there. All right, So the opposite direction is what we want, is the non-trivial thing. Okay, this is what we want to do. Okay, so let's set omega star to be omega 3r, and if I don't write the center, it's always this fixed center, capital X. Okay, intersect the set of y's such that y naught is less than x naught plus 6 m naught squared of n times r. Okay, so what's going on there? Remember that this was just the elongation factor for the box IR was 3 times this constant times r. All right, so what's going on here? Here's the picture. Here's sigma. I've got, sorry. It's not to scale. It should be elongated more, but I don't have room on the board. So this is going to be the omega 3r. And then I have omega 2r inside of that. Okay, and notice that since the elongation factor at scale r is 3 times this constant, this is the elongation factor for omega 2r. So what we're doing is just cutting off omega 3r at the height equal to the ceiling for omega 2r. Yeah. Is E sigma? I don't know why I wrote E. E is sigma. Yeah, thanks. Okay, so omega star is this part. Okay, it's the part of omega 3 where we cut it off at the height of omega 2r. All right. Okay, and then we're going to define. Again, I haven't drawn things to scale, but I'm going to define a set here on the lateral boundary of omega star that I'll call S prime. And S prime is defined to be S star. S star is what? Let me just write it out. It's the letter S of omega star. The lateral boundary for omega star is S star. Okay? Intersect the set where y naught is actually equal to this height, right? So across the top, and the t value or the s value is bounded between negative 8r squared and negative 5r squared. Okay, so notice that leaves gaps on the order of r squared here and r squared here. Because remember, for omega 2r, this backwards time value is t minus 4r squared, right? Because you square whatever the scale is. And here, it's t minus 9r squared. Okay? So this fits into this gap. There's a gap on either side here. Okay? And then we're also going to define a set here. This is S double prime. It's going to be a sort of a false ceiling below the ceiling for omega 2r. Okay, so this is going to be the set of, it's going to be inside of omega 2r, but we're going to cut it off where the height is maybe 1 unit down from here. So y naught is going to be x naught plus 5 times the same constant. Okay? All right, and now we have a thing that sometimes gets called Bourgain's estimate, which is just local non-degeneracy for, well, in Bourgain's case it was the harmonic measure, but for us it's the caloric measure. And it says that if, oh, by the way, I need to define one other thing. Let omega star be the caloric measure for the domain omega star, okay? All right, I'm going to take the pole at a point y. It's going to be an S double prime. And I take the caloric measure of S prime. This is going to be bounded by, from below by some uniform constant C naught, okay? Strictly positive. Omega star equals caloric measure. For the domain omega star. And here, this is holding provided that this point y is in the set S double star, or S double prime. Okay? So notice what's happening. This is saying, I'm realizing I'm not progressing nearly as fast as I had hoped. So I'm actually not going to prove this for you. I had planned to prove it. It's actually a consequence of sort of standard capacitary estimates, but there's a nice argument due to Bourgain that's just estimates for the fundamental solution plus the maximum principle. It's really clean and elegant. I would have liked to show that to you. But at least heuristically, what is going on, you're just saying that, right, the caloric measure, like harmonic measure, is a probability measure. So it has total mass 1. And all we're saying is that when the pole is close enough to a surface cube or surface ball, close meaning the distance is like the scale, the diameter of the surface ball, then basically you're already getting an ample portion of the full caloric measure, right? And except since it's a parabolic problem, we move it forward in time a little bit. Again, at the same scale. The scale here is always R, right? Capital R. All right? So that's all that's going on. Okay. I'm going to try an experiment today. Maybe for the sake of expediting matters. This seems faster than the squeegee. Okay. So now we're going to define two solutions. Some auxiliary solutions, V and W, as follows. Okay, V is going to solve an initial Dirichlet problem in omega 2R. So V is going to be identically 1 on the bottom boundary of omega 2R, and V is going to be identically 0 on the lateral boundary of omega 2R. And then W at a point Y is going to be defined to be the caloric measure for omega. So this is going to be defined in omega star, which contains omega 2R. All right, so it's going to be this quantity that I wrote up here. It's going to be omega star with pole at Y of the set S prime. Except now, for the moment, we're not restricting Y to live on S double prime. This could be anywhere in omega star for the moment. Okay? All right, so maybe I should draw you a little picture. All right, so I'll tell you what, instead of redrawing the picture, let me just augment this picture. Okay, so what are we saying? So up here, right, this is omega 2R. So we're saying V is going to be 0 up here. We're specifying that And of course, W is 0 there because W on the boundary of omega star is non-zero only here, and it's 1 here. Okay? And we're also saying that V is 1 here, but remember that H by hypothesis is also 1 here. So H equals 1 equals V along here. Okay? Along the bottom boundary of omega 2r. Okay? And of course, they all vanish on sigma. Okay? So V equals H equals W equals 0 on sigma. Okay? And remember also by hypothesis, H is always less than or equal to 1. Okay? The L infinity norm was 1. All right? So then by the maximum principle, we get that W is less than or equal to V is less than or equal to H in omega 2r. Okay? That's just straightforward maximum principle. Okay? On the other hand, by this Bourgain estimate, I have that 1 is up to some constant less than or equal to W. Remember, because W is that guy, which in turn, because of this fact, is less than or equal to V on S double prime. Okay, so the false ceiling there. All right. So therefore, by the maximum principle, we have that H up to some uniform constant is less than or equal to V in what I'll call omega double prime, which is omega 2r, but with a false ceiling. Okay? Omega 2r intersect this set where y naught is less than x naught plus 5 times that constant. Okay? All right. On the other hand, the backwards harmonic of Fabes, Garofalo, and Salsa does apply to V because it vanishes on the entire lateral boundary. Okay? Remember, the issue here compared to the Fabes, Garofalo, Salsa version is that we're no longer requiring vanishing on the entire lateral boundary. But for V, that happens. Okay? Right? V vanishes identically on S of omega 2r. All right? Okay, so therefore, H of AR plus is less than or equal to V of AR plus, right? Because H is less than or equal to V. All right, and since V satisfies the backward harmonic, this is in turn less than or equal to V of AR minus. But on the other hand, V was less than or equal to H. Okay? And then we're done. Okay. By the way, as a corollary, not of this theorem, but the corollary of the Bourgain estimate, we get Helder continuity at the boundary. Okay, which is this. Suppose that V is non-negative. V is a solution in, let's say, omega 2r. V is identically 0 on delta 2r. Then V of ys is less than or equal to, with implicit constants depending on the usual stuff, delta of ys over r to the alpha. Remember, delta is the distance to sigma, times the sup over, say, omega 3r over 2 of v. And here the alpha is also depending on n and m naught. All right. So I'm actually going to waste 2 minutes and prove this because it's quick and easy. Okay. So the proof. Okay. I'm going to normalize without loss of generality. This supremum is less than or equal to 1. Okay? I'm going to set W to be 1 minus V. All right? So W lies between 0 and 1 in omega 3 halves r. And W is identically 1 on delta 2r because V was identically 0 there. Okay? All right, so comparing this to the harmonic or the caloric measure of this set and invoking Bourgain, okay? We have that W is bigger than or equal to C naught in, let's say, omega r over 10, which says that V is less than or equal to 1 minus C naught, which is strictly less than 1 in, let's say, well, again, in omega r over 10. And then you iterate this, and you get Helder continuity. Okay? All right. One more basic fact that we're going to need, and I'd originally hoped to prove it for you, but I think I won't take time. I'll just state it and maybe give you a reference. The so-called Carlson estimate, it was Carlson's estimate in the harmonic context, but there's also a parabolic version. Here we suppose that U is non-negative. A solution of the heat equation in omega 2r, which is going to be omega 2r of some center x. And U vanishes on the corresponding surface ball or surface cube on sigma. Okay? Then the sup in omega r. Remember, omega r, this means omega intersect IR. The sup in omega r of u is less than or equal to, with implicit constants depending on the usual stuff, u, the value of u at the time forward corkscrew point. Okay, so this is in the caloric setting, this is a classical fact that goes back to Kemper. I had wanted to show you, there's a very nice, elegant proof, alternate proof, kind of recently, of De Silva and Savine. If you're curious, that's the place to go look, because it's short and easy. There's a proof in the elliptic case that often gets used due to Kefferle, Faves, Mortel, and Salsa. It's also the argument that Jerris and Koenig used in their paper on NTA domains. It's much more complicated. It's a contradiction argument, and it's rather involved. This De Silva Savine thing is clean and easy. So if I'd had just a little more time, I would have liked to have shown that to you. But okay, so we're just gonna accept this off the shelf. Okay. All right. So then I get to skip that, and I move ahead to the next thing that we're going to prove. This is also taken from Caffarelli and Salsa. Once again, we're going to let X be a point on sigma. Omega 2r, as usual, is omega 2r of x. We're going to have a non-negative solution that's continuous up to the boundary on omega 2r. It's a solution in omega 2r. And it's going to vanish identically on delta 2r. And we're also going to assume further that U satisfies backward Harnack in the sense of theorem 1, right? In omega 2r, okay? In the sense of the conclusion of theorem 1. So then the conclusion, the punchline is this: if we were to know qualitatively that the vertical derivative of U is non-negative in omega 2r, then in fact we have a quantitative estimate for the vertical derivative, and that is that it's actually comparable with implicit constants depending on the usual stuff. Well, this is at a point y, say. It's going to be comparable to U of y divided by delta of y. Once again, delta the distance to sigma. Okay? This is for y in omega r. So, yeah, right, we always have to cut things down in size a little bit. All right? Okay, so notice what's going on here. This is interesting. This direction, that this is bounded by this, is just standard interior estimates. Okay? That the derivative is less than the solution over the system boundary. Well, there's also backward Harnack here, because normally you would have to move forward in time, but backwards Harnack lets us move back to y itself. Okay? So the deep fact here is that we get an inequality going this way. Right? That's that this is bigger than or equal to this. All right. So the non-standard bit is to prove this direction. Okay? All right. So let's let y be a point in omega r. All right. Okay. And let's bear in mind that x in sigma means x naught is a of xt. All right. Okay. So now I'm going to set r to be y naught minus a of ys over, let's say, 10 m naught root n, the standard constant. Okay, so what's going on here? Here's a of ys, y, and s. And here's the point y naught ys. It lies vertically above that guy. Okay, and basically up to this harmless constant, r is like this vertical distance. And since we're in a Lipschitz graph, the vertical distance is comparable to the actual distance to the boundary. Okay, so note that delta of y is uniformly on the order of r. Okay? All right. And let's note then that, okay, so in fact, I'm going to solve here for y naught. This is just saying that y naught can be written as a of ys plus this constant 10 m naught root n times r. All right. So now I've got 10 m naught root n times r is y naught minus a of ys, which is, I'm going to subtract off and add in a of xt. Okay, so this part is less than this constant times capital R. That's just the definition of omega r, right? It's just the elongation factor for the box IR. Okay, and this part we're just gonna use. This is Lipschitz, so this is less than m naught times x minus y times the length of x minus y t minus s, parabolic length. All right, and with sort of crude estimates, this is going to be less than or equal to 5 m naught root n times r. Okay, just crudely think about where these are, which implies, notice that r, little r is less than capital R over 2. Okay? All right. So I'm going to define a time backwards point, set lowercase y prime s prime to be just y, but I'm going to move backward in time, s minus little r squared. Okay? And given a value mu between 0 and capital M naught, I'm going to set y prime of mu. I'm sorry, I apologize for that notation. It looks like I'm taking a derivative with respect to mu. No, it's just defining the point because it's going to be relative to this y prime s prime. Okay. It's going to be A of y prime s prime plus mu r. That's the vertical variable, and then y prime s prime. So at some point elevated above the point on the graph, which would be, if mu equals 0, this would be exactly the point on the graph. Okay. All right. And so therefore, notice also again, because we're in a Lipschitz domain, the vertical distance is like the actual distance. So delta of y prime mu is on the order of mu times r. Okay. Okay. All right. So notice that since the point y by assumption was in particular, it's in omega r, so in particular, it's in IR of the point x, we therefore have that yi prime minus xi, this is coordinate wise. Remember, y prime is the same as y, so this is yi minus xi. And this is less than r, this is for all 1 less than or equal to I less than or equal to n minus 1. And s prime minus t to the 1/2 is s minus r squared minus t to the 1/2. And the triangle inequality says that that's less than r plus s minus t to the 1/2, which is less than r plus. And remember, in IR, this quantity to the 1/2 power would be less than capital R. And little r was less than capital R over 2. So this is less than 3 capital R over 2. All right, which tells us that, therefore, y prime s prime is in a slightly fattened cube. Right, I'm using cube for the n-dimensional cubes, centered at xt. All right. Okay, and so therefore, for all 0 less than mu, less than or equal to m naught, I've got that A of y prime s prime plus mu r, right, which is the vertical component of that guy, minus A of xt is less than mu r plus, it's just that plus the difference here, and I use that, this is, again, a parabolic Lipschitz function. Okay, and remember mu is less than m naught, and again, just the size estimates that ys prime is in this cube centered here. Altogether, just crudely, this ends up being less than, let's say, 4, maybe strictly less than 4 m naught root n times r. Okay? So in particular, y prime of mu, whose vertical component is that, all right, is lying below, remember, this is the x naught component of the point capital X. So we're below, and this is the ceiling for I2R with that center, okay? So this is in, sorry, it's well below that ceiling. It's actually below the ceiling for omega 3 halves R, okay? So this is in omega 3 halves r of x. Okay? And this is true for all mu's here. If you'll indulge me for about 1 or 2 more minutes just to finish this proof. Okay? So then by Hölder continuity at the boundary, and the Carlson estimate, and backwards Hölder, we get that u of y prime mu tilde, for a mu tilde that's going to be small enough to be chosen, is less than or equal to, this is Hölder continuity at the boundary, the distance of that guy over r to the power alpha times u evaluated up above the boundary point a of ys, ys. All right? And this is going to be less than or equal to, remember, this is comparable to mu times r, we observed. So this is mu tilde, sorry. So we get mu tilde to the alpha, and we get u, right here we're using backward Harnack, to go backwards in time to y prime of m naught. And for mu tilde small enough, this is less than 1/2 times this value. All right, and now we're ready for the punchline. So then by backward Harnack, we get u of y is less than or equal to, right, backward Harnack tells us that this is controlled by this. And then this is going to be less than or equal to this thing with some constant. All right, which is of course less than or equal to, since 1/2 of this controls this, that's the same as saying that this is less than u of this minus u at that point. Okay, and then we just integrate. In mu, from mu tilde up to m naught, that introduces this derivative. Remember, by hypothesis, we're assuming this is non-negative, so we can apply Harnack to it. Okay, so then this is less than or equal to r times dy naught of u of y, which is like, remember we observed that that's r is like delta of y times dy naught u of y. Okay, and that does it. All right. Okay, sorry for running over. Let's get coffee.